Do you believe in ghosts? While the response to the question varies from person to person, scientists using the Large Hadron Collider found something ghost-like in the particle accelerator for the first time. What have these scientists discovered? Why is it referred to as a ghost? Should we be scared of this particular discovery? In this video, we bring you all the details about what scientists just announced they found in the Large Hadron Collider for the first time ever. Did you know that while you sit and watch this video, billions of particles are passing through your body? And there is a reason you do not feel these particles passing through you and are not harmed. The Large Hadron Collider have revealed just what these particles are and other amazing details about these particles. But what is the Large Hadron Collider? This invention is the largest, most powerful particle accelerator in the world. If you don't know what a particle accelerator is, they're used to collide energetic particles to investigate the structure of the atomic nucleus. They were invented in the 1930s and have helped scientists to understand many aspects of physics. They work by speeding up and increasing the energy of a beam of particles by generating electric fields that increase the particle's speed. Magnetic fields direct and focus the particles. In the Large Hadron Collider, or LHC, two high-energy particle beams shoot about at near the speed of light before they are made to collide. After the collision, the beams travel in opposite directions in separate beam pipes or two tubes maintained at ultra-high vacuum. The LHC has electromagnets made from coils of special electric cables operating in a superconducting state. This ensures that they efficiently conduct electricity with little to no resistance or loss of energy. To achieve this, the LHC cools the magnets to minus 271.3 degrees Celsius. That is colder than outer space. The LHC employs thousands of magnets of different sizes to control the beams inside the accelerator. It has a 27-kilometer ring that is buried underground at CERN. The decision to construct the LHC underground was made to save on cost, as it was less expensive than acquiring land on the surface, reduce the effect on the environment, and takes advantage of the Earth's crust as a good shield for radiation. The construction goes as deep as 100 meters under the Earth's surface. The LHC cost $4.75 billion to construct and took a decade. The bulk of the fund came from European countries, including Germany, the UK, France, and Spain. Interestingly, CERN wants to build a new super collider at the cost of $23 billion, which will be 100 kilometers long. Fun fact, the annual energy consumption of the LHC is equivalent to one-third of the power consumption of the households in the canton state of Geneva. However, the investment has been worth it thanks to the many discoveries that have been attributed to the LHC. One such achievement is the discovery of ghost particles known as neutrinos. Neutrinos are some of the tiniest particles ever discovered. They were spotted during a test run of the LHC. This landmark achievement was made possible through the joint work of CERN's forward search experiments. But what are neutrinos, and why is there so much excitement about them? Even though neutrinos are very elusive, which is why they are called ghost particles, they are produced by different nuclear processes. Neutrino means little neutral ones. It is apt because they do not possess an electrical charge. Out of the four fundamental forces of the universe, neutrinos interact with only two, and these are gravity and the weak force, the force that is responsible for the radioactive decay of atoms. Neutrinos have no mass and are able to travel at the speed of light. A lot of neutrinos were produced in a fraction of a second after the Big Bang, but of course numerous neutrinos are still being produced today. They originate from the nuclear hearts of stars inside particle accelerators and atomic reactors. They also come into existence during supernovas and in the radioactive decay of substances. Scientists say neutrinos outnumber protons in the universe 1 billion times. Even though numerous neutrinos have been a tough nut to crack for scientists, this is because of their ability to remain neutral to most substances found in the universe. That is why billions of them can pass through a square centimeter of your body without you noticing. They just stream through most matter like light rays passing through a transparent window. Neutrinos carry a wealth of information as they travel through the universe, unlike other particles that may be distorted by their interaction with different matters. Our understanding of neutrinos means we know the beginning of the universe better. Neutrinos came to be discovered as scientists tried to solve the puzzle of a process known as beta decay. The thing about beta decay is that it seems to defy two fundamental physical laws: the law of conservation of energy and the law of conservation of momentum. They discovered that during beta decay, the final configuration of particles appeared to have slightly too little energy, and the proton stood still instead of moving in the opposite direction to the electron. A physicist named Wolfgang Pauli theorized in 1930 that an extra particle might be escaping the nucleus and carrying along the missing energy and momentum. However, Pauli himself knew that the particle he had postulated could not be detected. He said to a friend, "I have done a terrible thing. I've postulated a particle that cannot be detected." Our Sun produces colossal numbers of neutrinos, and many of them end up bombarding the Earth. Scientists came up with different detectors to catch these neutrinos, but their experiments could only detect 1/3 of the neutrinos they had predicted. For many years, scientists have tried to solve this issue. However, they were overlooking one simple fact. Neutrinos came in 3 different flavors. The ordinary neutrino is known as the electron neutrino. In addition are 2 other types known as a muon neutrino and a tau neutrino. As they pass through the distance between the Sun and the Earth, neutrinos oscillate between these 3 types. This is why the earliest neutrino experiments, which were only designed to search for one flavor, kept missing 2/3 of their total number. The discovery at CERN was the first time neutrinos were found inside the LHC or any particle accelerator at all. The ensuing excitement was because the breakthrough opened a completely new window through which scientists could investigate the subatomic world. Being able to detect neutrinos inside the LHC will help scientists further understand their role in the universe. As we previously stated, prior to the discovery by the LHC, scientists had managed to capture neutrinos before. There had been the Japanese Super Kamiokande detector, Fermilab's Mini-Boon, and the Antarctic Ice Cube detector. All of these managed to detect neutrinos using a procedure known as the Cherenkov radiation. This Cherenkov radiation method uses a principle similar to a plane traveling faster than the speed of sound, which creates a sonic boom. The particle is made to move through a light-slowing medium. This creates a faint blue glow in its wake, which scientists look out for. However, these experiments leave scientists with a lot of questions, even though they can detect signatures of neutrinos coming from the Sun. For example, scientists can't tell the types of high-energy neutrinos that are produced when these particles smash into each other in a typical particle accelerator. To be able to find this type of artificially created neutrinos, the scientists at the Phaser Collaboration created a new detector, which they named Phaser Nu. How does Phaser Nu work? The Phaser Nu is made up of dense metal plates of lead and tungsten with multiple layers of light-detecting gunk called emulsion sandwiched between them. The neutrinos will first crash into the atomic nuclei in the dense metal plates to produce their particle byproducts. Then comes the emulsion part, which works just like your normal photographic film. The emulsion reacts with the neutrino byproducts to imprint the traced outlines of the particles as they zip through them. What follows is that the researchers develop the emulsion and analyze the particle trails left behind by the neutrinos. This allows the physicists to figure out that some of the marks were produced by particles. This method even allows scientists to identify the type of neutrinos detected out of the 3 possible types. This confirmed that they had not only picked the right spot inside the gigantic ring to detect neutrinos, but that their new detector was actually able to see them. But the scientists are not stopping here. Now that they've produced a working detector, the physicists are now building an even bigger version of it. This version will be more sensitive in detecting the neutrinos. We'll also be able to detect the difference between neutrinos and their antimatter opposites, antineutrinos. When the LHC powers up again, they plan to use the detector to study the neutrinos produced by the particle accelerator in depth. The new detector will weigh over 1,090 kilograms, which is many times more than the 29 kilograms of the current version. With the new powerful detector and its prime location at CERN, we expect to be able to record more than 10,000 neutrino interactions in subsequent runs of the LHC. They hope to detect the highest energy neutrinos that have ever been produced from a human-made source. And neutrinos are not the only things the phaser scientists are working on. The team is also working on an experiment to detect hypothetical dark photons, which physicists think could be intimately connected to dark matter, the mysterious, non-luminous substance believed to account for roughly 85% of the matter in the universe. Let's hear what you think of these ghost particles in the comment section below.